And let's move on without further ado to our final speaker, who is Beñat Mencia Uranga from Multiverse Computing, and he will speak about SchrödingeRNN. So please take it away, Beñat.
Hello, everyone. First of all, well done, everyone, making it to the last talk of this conference, and thank you, organizers, for making it happen. I thought it was very well organized and went smoothly. Okay, so let's start. So today I'll be talking about generative modeling of raw audio as a continuously observed quantum state. This is some work I did during my PhD in collaboration with Austin Lamacraft, who gave a talk on Wednesday on quantum ground states using reinforcement learning. So the outline of this talk is the following. I'll start talking about the goal of the project, then say a couple of words about quantum mechanics and probabilistic generative models. Then I'll move on to give some details about our model. After, I'll say something about the learning process, and I'll end my talk showing a couple of results. So the goal of this project is to build a generative model for raw audio. Concretely, we want to learn the joint probability distribution of a given data set. Raw audio data happens to be very high dimensional. To give you an idea, a minimum quality sound would contain 16,000 samples per second. And so it's a priori a very costly problem. Whenever you build a generative model, of course, you want to find suitable inductive biases for the problem at hand. And in this work, we search for these inductive biases in quantum mechanics. So a central object in quantum mechanics is the quantum state, which contains all the physical information of the system it describes. This, and for the purpose of this talk, you can think of it as a complex vector. This quantum state follows a kind of wave equation, which is the Schrödinger equation. So here, the H operator is the Hamiltonian operator of a given system. And importantly, in this context, this quantum state defines a probability distribution. Let's say we want to know the probability distribution of all possible outcomes of the measurement of a given observable. Let's say, for example, momentum k in red or position x in green. What we would do, we would, as shown here, project the quantum state into the basis states of a given observable, and then take the modulus square. So this is the connection between quantum mechanics and, in this case, probability distributions, which we will use to model our raw audio. So raw audio is continuous data, and furthermore, it's wave-like. And it turns out that quantum mechanics is full of probabilistic models of wave behavior. So a priori, there is a, let's say, pretty good excuse to explore this avenue of connecting these two. So our model takes the form of a stochastic Schrödinger equation. The physical system you should keep in mind is the one that is roughly illustrated down here, where we have a yellow atom described by quantum state psi, and this atom is coupled to an external field with which it can exchange photons. And furthermore, one can measure the current of photons in this external field. And we will be thinking of raw audio signals, the blue signal shown here, there's an example, we will be thinking of them as the outcome of a continuous measurement on such physical system. And for those that are familiar with tensor networks, the quantum state described in such a physical system happens to be equivalent to a continuous matrix product state, which is a kind of tensor network. So let's do some math. We will model these raw audio signals as a stochastic process described by this stochastic differential equation shown here. The second term is Brownian motion, and the first term contains a expectation value defined here in the right side with respect to the quantum state. Now the quantum state follows this equation of motion, which is it's a Schrödinger equation, stochastic, as I said before. The stochasticity enters here in the second term, where we have this random process driving the quantum state. So I just said that we can describe can describe our atom using a quantum state, or what we call a pure state, but we can also use what is called a mixed state. And in this case, what we would have is that instead of having a complex vector describing the system, what we have is a complex matrix. This has its own physical meaning, namely adding an extra degree of uncertainty about the system. But the implications here are that we have a more complex model, and so it's more costly. On the one hand, instead of time evolving a complex vector, we are time evolving a complex matrix. And furthermore, since we will be learning the initial values of this quantum state, this will increase the number of learning variables. Yeah. Okay, so because we are considering continuous processes here, the probability density associated to a continuous process is not a normalizable object. And so if you want to do maximum likelihood, you need to define a normalizable object. And typically what is done is one optimizes the so-called Radon-Nikodym derivative, which is nothing but this ratio of probabilities. And the trick here is that our model contains the learning variables here in the numerator, but the process in the denominator, which is the process of Brownian motion, doesn't depend on the learning variables. And so the optimization of this object will yield the optimization of the probability density of our model indeed. And the expression is in our case, for our model, the expression of the Radon-Nikodym derivative is the one shown here. The loss function, well, we want to minimize the negative log likelihood, well, ratio of likelihoods actually. And so the loss associated with a given, a single signal is the first line here. But of course, we want to maximize the likelihood of the whole data set. And so we will assume that our data set is ID, and we will optimize a batch at a time from our data set, which is shown in this second line. The learning parameters are, well, actually the Hamiltonian matrix describing our system. This is given by this matrix R. We have this vector H. As I said, we will also be learning the initial values of the quantum state that we time evolve. And then we have a amplitude parameter A here. And the hyperparameters, first, it's the bond dimension, which is the dimension of the Hilbert space of the atom. And then we have the sigma hyperparameter, which sets the strength of the deterministic part of the Schrödinger equation compared to the stochastic part. So in order to compute the stuff, we need to discretize and integrate our stochastic differential equation. We will use the simplest integration scheme, the Euler-Maruyama. Then the stochastic differential equation becomes this discrete stochastic process shown in the first line. The equation of motion for the quantum states are the ones shown here. And the loss function, we just substitute the integrals by sums, and that's what you get out. I wanted to make explicit that actually our model has the structure of a autoregressive recurrent neural network. With the hidden state that appears in recurrent neural networks is in this case incarnated by the quantum state that follows this nonlinear evolution, or has this nonlinear update equation. And the nonlinearity appears in the second line, which corresponds to the normalization of the quantum state in its discrete step. And furthermore, the structure of causality of the joint probability of events corresponding to a given signal has the structure is such that it's a autoregressive model. So a couple of results. Okay, so the way we test the performance of our model is we create a data set from a known probability distribution. Then we use this data to train our model. And then we use the trained model to generate new data. Now we compute statistical quantities with the generated data such that we can compare this with exact expressions, exact analytical expressions for these quantities. And that's how we judge the performance of our model. In this case here, I'm showing some results of where we train our model using Gaussian processes. We define our Gaussian process, our stationary Gaussian process using the the covariance matrix shown here, which this is called, by the way, a maternal spectral density mixture. And we train on 2 different Gaussian processes with capital M equals to 1 and capital M equals to 3. And the results are shown here. Here, the results are showing the blue line is the experimental, the experimental covariance. The yellow line is the exact covariance. And as you can see, in both cases, the match is fairly good. Furthermore, we also do experiments on filter Poisson processes. The filter Poisson process is shown here with this Poisson process, and the pulse, the shape of the pulse is defined here with this phi function. And here again, we compare the experimental correlators with the exact correlators. We look at these 2 correlators defined here on the right-hand side, and this is because unlike Gaussian processes, filter Poisson processes are not time reversal symmetric processes, and for such processes, these 2 correlators should differ. And as you can see here in the when we show the exact expression for the correlators, there is a difference. On the right-hand side, we are showing the experimental result. As you can see, somehow we failed to capture this difference between these 2 correlators, but we are able to match one of them. Not sure why we failed to capture this difference. And to conclude, summary, we've built a generative model for raw audio based on stochastic Schrödinger equation. As far as we are aware, this is the first time where continuous matrix product states are used in machine learning, and we obtained some good results on synthetic data. Looking forward, it would be interesting, first of all, to test the performance of this model on real data, which we didn't do, and to benchmark this model against others. It would be good to have a feeling on how we were making a point that there is a good excuse to search for these suitable inductive biases in this context. It would be nice to check whether this is right or not. And finally, it would be very interesting to see how the quantum entanglement of the learned wave function or quantum state is related to the structure of correlations in the generated samples. This is it. Thank you very much.
Awesome. Thank you, Beñat, for this great talk and for being completely on time. I mean, it's up to the second. So one question for Beñat that was asked in the Q&A was that, so why is Schrödinger evolution considered, but not another ODE for the evolution of time series data? And maybe I would want to add to that. So would your ideas, do you think they can be transferred to other dynamical systems also?
Yeah, so, well, the reason why we chose the Schrödinger equation is because, well, because we are quantum physicists, we know a lot about it, and so it's a natural place for us to search, given the set of differential equations out there. Furthermore, we're making a point that the quantum physics is a place where probabilistic wave-like models appear, and so this is, I would say, a great reason to explore this avenue in quantum physics. But that's right. You know, surely there are many wave equations that would be suitable for wave-like data, and so yeah, I have nothing to say about. Well, I know nothing about other models doing this. I would just say that there is a good reason why to explore the Schrödinger equation.